Alright guys, today we're going to cover section 7.1, exploring exponential models. So we start with the definition of an exponential function. This is a function with the general form y equals a times b to the x. Notice here your exponent is a variable. Exponential functions will always have a variable as an exponent. The other important things here is a cannot be 0. The reason that a can't be 0 is because if I plug in a 0 and multiply it by anything else, I'm going to end up with an equation y equals 0, which would be a linear function, not an exponential function. The guidelines we have to use for b are that b has to be greater than 0, meaning it's a positive number. Also, b cannot equal 1. So here's what that means. That means that b is a positive number and that includes fractions, decimals, and whole numbers, except for the number 1. So now at the bottom here, we're going to graph an exponential function. And before we graph it, I want to identify a few parts of this. I want to identify the value of a and the value of b. So one thing to know is that b is always the number that is raised to a power. Okay? It's always the number that is raised to the power of x. So in this problem, my b value is 2. A is the number that's multiplied in front of that. Well, this problem doesn't have a number written in front of it. So it's understood to be a 1. So my a value is 1. So now we'll come back to what that a and b value tell us in just a few minutes. But in the meantime, let's make a table so that we can graph this. I'm going to pick a few negative values for x and 0 and a few positives. So now when I plug those values in, I end up with y equals 2 to the negative 2, but you can't have a negative exponent, so we have to fix that part. Remember, you're going to move it to the bottom of the fraction and your exponent becomes positive. So 1 over 2 to the positive 2 gives me 1/4. So when x is negative 2, y is 1/4. Next, when I plug in a negative 1, y equals 2 to the negative 1, fix your negative exponent by moving it to the bottom, and I end up with 1/2. So when x is negative 1, y is 1/2. If I plug in 0, 2 to the 0 is 1. Plug in 1, 2 to the first is 2, and then 2 to the second is 4. I can plot these points and sketch in my graph. So negative 2, 1/4 is about right there. Negative 2, 1/2, 0, 1, 1, 2, and 2, 4. So here's what my graph looks like, and I'm just going to estimate and continue here. Now on the left side, we've got to talk about whether this graph is ever going to touch that x-axis or fall below it. And here's the thing, it doesn't matter how small of a number you put in for x. You know, if I put in a negative 10, That's y equals 2 to the negative 10, which is 1 over 2 to the positive 10, which is still a positive number. I'm never going to get a negative number. I'm never going to get 0. So my graph is going to continue to forever get close to that x-axis, but it's never actually going to touch it. It's never going to cross it. So that x-axis is what they call an asymptote. It is a line that a graph approaches but never touches or crosses. So in this problem, our x-axis is an asymptote. Now, we're going to do a couple more graphs, and then we will talk about the A value and the B value for each of those. And then we'll compare it to the A value and the B value of this one and talk about what that tells us about our graphs. Okay? So here's the next one. What I need you to do is I need you to sketch a graph of y equals 4 to the x and y equals 1/3 to the x. Okay, so you can make your own chart, or you can grab your graphing calculator and punch them in there. Well, let me get it typed in here first. So y equals 4 to the x power. If I graph it, here's what it looks like. And you can see it looks like the graph is going to actually touch the x-axis here, but that's because of the pixel size and the resolution on these calculators. It's not, you know, good enough resolution to show that it gets super, super close but never touches. So it's a little bit deceiving. But here's what your graph looks like. It looks a whole lot like the last one that we did. So I'm going to go back to my paper and sketch it. And this is just a sketch. It doesn't have to be perfect. For this one, my A value is 1. My B value is 4. So what I'd like to do before we go on to part B is compare this graph to the graph we did a minute ago of y equals 2 to the x. So if I go back here to my y equals, and I'm going to go down here and type in y equals 2 to the x power, and mine's going to graph it in red so you can see them side by side. So far everything's looking about the same. looks like they have the same y-intercept, but the blue graph that was 4 to the x is a much steeper graph than the red curve that is y equals 2 to the x. So let's go back over here and see what we can determine about that. Okay, so for both of those graphs, my y-intercept was equal to 1. Well, guess what? That is your A value. The value of A will always tell you what the y-intercept is. The B value, what I want you to notice about it is that when it is a bigger B value, it is a steeper graph or a steeper curve. Okay, so to sketch these, if you know what the y-intercept is and about how steep it is, you just sketch it in. It doesn't have to have a whole lot of points on it. But now, part B over here is going to change all that just a little bit. So you can make a table for it just like we did for the very first problem, or we can go back to our calculators. And I'm going to clear these two graphs out and now type in y equals 1/3 to the x power and graph it. It's a little bit different. And it's taken just a minute. There it comes. Notice this one turned around the other direction. So we're going to go back, sketch this on my paper, look at the A and B values, and see if we can, kind of draw our own conclusions here. The graph for this one, the y-intercept was still 1. Which was my A value. But this time it curved the opposite direction. Notice your B value. When B falls between 0 and 1, it changes direction. And this is where math meets science. These two graphs represent exponential growth and exponential decay. So here's what your book tells us about growth and decay. Exponential decay always goes this direction. And your B value for exponential decay is always between 0 and 1. Exponential growth always goes this direction, and that is when your B value is always bigger than 1. And once again, they tell you that your x-axis is an asymptote. That is true for growth or decay. So now, once again, here's a definition for asymptote if you did not get it before. All right, now let's look at a couple of equations and figure out from the equations whether our function is a growth or decay function. And by the way, this box here explains everything that I just put on the last page for you, that I put on the graphs of the growth and decay functions. All right, what they want to know is whether or not this problem represents growth or decay, and it also wants to know the y-intercept. Well, to figure out the growth or decay part, I need to look at the b value. So in this problem, my b value is 0.95, which is between 0 and 1. So this represents decay. Now, to figure out the y-intercept, remember we have to look at the a value. So my y-intercept is going to be 12. For part B, my b value is bigger than 1, so this is growth. My a value is 0.25, so I know that my y-intercept is 0.25. Now part C, it looks like it's a word problem and looks like it wants you to do something. But all it wants to know is whether it's growth or decay and what your y-intercept is. So I'm going to put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. Well, every year I'm going to have more money in my account than I started with. So this represents growth. And my y-intercept, that's my starting point. That's how much money I started with. So my y-intercept here, if I was going to graph it, would equal 1,000. Now, something I want to do with this problem, and I'm going to grab an extra sheet of paper here to do it on, is to go ahead and see if I can write the exponential equation for this problem. So I know, based on this information that we've got here, it's growth. My y-intercept is 1,000. So when I write the equation, y equals a times b to the x, I know that a is 1,000. And what's my b value? In almost every class I've taught, everybody wants to tell me that b is 0.05 because that's what the interest rate is. But if b is 0.05, that's a number that's between 0 and 1. So that would represent decay. And we just discussed that savings accounts are growth. So there is a formula that you're going to use. You're going to take and add 1 plus the rate, and your b value is actually 1.05. Okay? My formula for b is going to be 1 plus the rate. So now, to write my equation, all I do is plug in my information. Y equals 1,000 times 1.05 to the x. And now we could evaluate this. So if I told you I wanted to know how much money we had in this account after 6 years, like, yeah, we're going to go to 6 years instead of 4. So if I want to know about 6 years, then what I'm going to have is 1,000 times 1.05 to the 6th power. And that will tell me how much money I have in my account after 6 years. So I can take and just type that into my calculator over here. Okay. Once I do, I'm going to end up with $1,340.10. And I automatically round it to 2 decimal places because it is money, and money always rounds to two places. So now we're going to do a couple more. What if I ask you to do this for 8 years and 10 years? You're going to plug it in the exact same way. I'm going to pause here for just a second, give you a second to type those in, round your dollar amounts, and then I'll put mine up here. So when I plug all of this in for 8 years, I end up with $1,477.46. For 10 years, I end up with $1,628.89. Now, what if I wanted you to make a list for me of how much money was in the account for every single year, starting with the first year? So I start with 1,000, after year 1 how much, after year 2 how much, and go all the way up to 25 years to see how much you have in there. Well, that would be a real pain to do. So what we're going to do is we're going to use our graphing calculators to help us create a table like that. So on my calculator, open up your y equals, and let's clear out what's in there. And I want to go ahead and type in my 1,000 times 1.05 to the x power. Do not put a number in for x. We're going to leave x as a variable. Just leave it there. And now if you look at your table, here's what you've got. X represents how many years. Y tells you how much money. So if we go down to 6 years, well, I don't see 2 decimal places. It's because of the size of my columns. But if you will arrow to the right, down at the bottom of your screen, it actually gives you a big long decimal that you can round to 2 decimal places. So if I were to ask you how much money is in the account after 15 years, all you have to do is go down until your x is equal to 15 and look at the y column. At this point, we will have $2,078.93. Okay, so after 15 years, that's how much money I have. So next thing I want to know, and we're going to use this table kind of in reverse, I want to know how many years before we have at least $2,500. So what we're going to do is look at our table in our calculator, and I want to go down that Y column until I see something bigger than 2,500. Well, see, at 18 years, I've only got 2,406 and some change. But at 19 years, I have over 2,500. I have $2,527. So the answer to that previous question would be, what was it, 19 years? Yeah. That would be 19 years. So now, I want to show you this formula the way your book gave it to us. They changed one thing in the information that we were just looking at. Okay, so here's the equation they give us. Okay, instead of saying y equals a times b to the x, they changed y to a of t, because that's the the amount of money after a certain period of time. Leave your a, that's your initial starting amount. And then b, remember, we said use the formula 1 plus r. And then instead of an x, they made my exponent a t. And that's just because that's the amount of time we're going to leave it there. So now, we've got a couple of other questions here that deal with the same savings account, but we've kind of covered everything that's in it. It just gives you a chance to work with that table a little bit more. So for now, we're just going to leave it, and we'll revisit it again next time. All right, I hope it helps.